So today we are going to talk about another another class of supervised learning technique which is used for classification. Okay, so we will talk about classification trees. So in classification trees, we study the problems. So which are posed as classification problem. Okay, so the problems we study, those are the classifications problems, and if we want to implement the solutions of those problems using classification trees, then we can have a number of choices. So a number of choices means if we talk about the approaches of classification trees, then we can have decision tree. Okay, and decision tree is having a number of variants like ID3, okay, card, then we can have C 4.5. So these are the different variants of decision tree. So these decision trees decision trees are used for classification uh, of the examples. Now a classification task. Now the classification, when the classification task is done by decision tree algorithm, then the decision tree algorithm assign the labels to the examples. Okay, so if we use an unknown example to have the classification level or the class information, then we can use the decision tree, and decision tree can be used for both binary classification as well as for multi-class classification. Okay, so for both the purposes, for we can use the decision tree. Now, among these three variants, ID3, CART, and C4.5, so we use these variants for some specific reasons. That means, according to our requirements, uh, we can use these variants, and we can have some specific decisions which are generated in the output. So, let us consider a decision tree. So, suppose we deal with two-dimensional data x1 comma x2. Here we can write at2. At2 means 2 means here two-dimensional feature vector. Okay, so in the feature vector we are having two attributes x1 and x2. So here x1 is one feature and x2 is another feature. Okay, now if we consider a feature vector like suppose we are considering a feature vector d, then d will have this two features or two attributes x1 and x2. Okay, and here x1 x2 belongs to R2. That means we are using two-dimensional data for classification purpose. Now let us take an example of a classification tree, and from that we will try to understand how classification tree works for classification. Okay, so let us consider a simple example. If x1 is less than, suppose some value we are taking 0.129, then further whether it is true or not. So we are asking the question if x1 is less than 0.129 or not. Okay, so if the question, if the answer is found to be yes, then we can have certain output. Okay, and if the answer is found to be no, then we can have another output. So let us consider here now, if the x1 is less than 0.129, then we will go for x2 and we will check whether if x2 is less than let's say 0.101. Okay, now if x1 is less than 0.129, then if the answer is for if the if this condition is found to be true, then we will go on this branch. Otherwise we will go to the branch which is labeled by no. Okay, okay, so in this way, every time we are trying to check a certain condition based on which we will go to the branch which is labeled by yes, or we will go to the other branch which is labeled by no. Okay, so that means at the root of this decision tree or the classification tree, we enter the data. Okay, data means here the feature values. Okay, since we are talking about two-dimensional feature vector, therefore here we will have the values for x1. Okay, we will have a set of values for x1, we will have set of values for x2. So if we are talking about the n number of examples, then we will have n number of values for x1, n number of values for x2. Okay, and x1 x2 are two different attributes in this feature vector. Now at the root of this decision tree or the classification tree, we enter the input. Okay, we enter the feature values, and then we checked whether this feature value is found to be, or it meets some certain condition or not. If it does not meet the certain condition, then we will take take a branch which is labeled by no. Otherwise we will take another branch which is labeled by yes. That means if the answer is found to be yes, then we will go to a branch, and if the answer is found to be no, then we will take another branch. Okay, so that means from this classification tree, one thing is understood, that whatever the classification problem that we will deal with, every time we need to enter the input data to the root node. Okay, so here we will have the root node. These are the non-leaf nodes. Okay, these are the non-leaf node. This is our root node. Okay, now, so root node considers the input data for different attributes. Okay, now what is the task of non-leaf node? Now non-leaf node, now when the when the decision coming out from the root node or some other non-leaf nodes, then this non-leaf node is used to split the data further. Okay, split the data further based on some splitting parameter. Okay, so we will talk about the splitting parameters in subsequent topics, and here we need to understand what are the different tasks of these nodes which are available in the classification trees. Okay, so here the non-leaf node is responsible to split the data which is coming out from the root node, and according to the decision which is made at the non-leaf nodes, so we further classify the data, and we will get another set of branches for non-leaf node or leaf nodes. Okay, now let us consider here at this stage or at this level, there is no further classification, or there is no further splitting of the data which is coming out from this non-leaf node. Okay, and here we are getting the leaf node. So here all the nodes are found to be leaf node. Okay, at this level. So we may have n number of levels in this classification tree. So at the end of the classification tree, we will have a number of leaf nodes. Okay, and leaf nodes will have some attribute value, and this attribute value denotes some decision, like whether if we are dealing with the binary classification, then obviously here we will have generate some class levels. Either it is 0 or 1, either it is yes or no, either it is some positive or negative. So in this way we can classify the data which is entered through the root node. Okay, and it is propagated through these non-leaf nodes. Okay, and non-leaf nodes is responsible to split the data further. Okay, and leaf node is responsible to assign the class level to a particular value of the attributes. Okay, so here we can have more than two attributes, or just with one attribute we can classify the uh, input data, and we can put a label to this example. Okay, so this is the basic so this is the preliminary concept about classification trees. Now we will talk about some parameters that we can use in the classification tree. So now it is clear to us that there are three different types of node in the classification tree. One is the root node, another is non-leaf node, and at the end we will get the leaf nodes. Okay, and root node is responsible to consider the values of the attributes. Okay, and non-leaf node is responsible to split the data further, and leaf node is responsible to assign the class level to an unknown example. Now let us consider here T is a leaf node. Okay, and X, capital X comma Y is a datum. Okay, datum, so that enters the uh, leaf node. That means this data is coming out from some non-leaf node or intermediate node. Okay, and we can denote. So when this data will enter the leaf node, which is coming out from some non-leaf node, so we can represent this by x belongs to small t. Okay, so here small t is the leaf node, and here x, which is coming out from some non-leaf node, and here we can consider another parameter nc, so which represent the number of training data. So we can write number of training data of class C. Okay, of class C. Now we can consider another parameter NTC. So what is NTC? NTC is the number of training data of class C that enters node T. That means here NTC represent the number of training examples of class C, so that enters node T. Okay, so let us consider here we are dealing with C number of classes, capital C number of classes, and small c is small c represent a particular class. Okay, or we can say cth class. So here NTC is the number of training data of class C that enters the node T. Okay, we can consider one more variable. So we can write NT equals to summation over NTC I equals to 1 to capital C. Okay, so or you can know small c. Okay, so I equals to 1 to small c. So here we can get, so this represent the total number of training data, that enter node leaf node T. Okay, so this NT represent the total number of training data that enter node leaf node T. Okay, now what will be the probability that a datum enters node T, given that its class information is C or class level is C? So this can be estimated by the proportion of training data and training data of the class C which enters it. Okay, that means here we can get the probability of X which enters the leaf node T, given that the class information is C. Okay, so therefore we can write, so p cap of X belongs to T given class information C, small c. Okay, and this is given by NTC divided by NC. Okay, NTC divided by NC. Okay, so you need to understand that using these three parameters NTC and NT, so we can estimate the probability of some data that enters the lib node T. Okay, so here what we are considering here, we are considering this, the class information is given to us, and we need to estimate the probability of the data that enters the leaf node T. Okay, so that is why we are writing the probability p cap of X belongs to T. Okay, X belongs to T given Y equals to small c, and this probability is given by NTC divided by NC. That means the number of training data of class C that enters node T divided by total number of training data that enter node T. So we can use this estimated probability to further estimate the posterior probability of a data of class C, given that it enters node T. Okay, so using that estimated probability, we can further estimate the posterior probability that a data belongs to class C, given that it enters the leaf node T. Okay, so therefore, what we can write? So we can write probability p cap of Y equals to C given capital X belongs to T. So here we are interested to estimate the posterior probability of the data that belongs to class C given given the data that enters lymph node T. Okay, so therefore we can write, so this is given by probability of X belongs to T given class information C, and this is multiplied with probability of Y equals to C. Say here the probability Y equals to C is prior probability or marginal probability, and this is divided by the evidence. Okay, so this is divided by evidence. Okay, so here the evidence is nothing but the joint distribution of X belongs to T and Y equals to C. Okay, so here we can write where probability of X belongs to T or evidence equals to, so summation over, we can write D equals to C. Here D is the index which is used to denote a particular class. Okay, so D equals to 1 to capital C. Now we are writing the joint probability distribution. P cap of X belongs to T, Y equals to D. And in place of this joint probability, we can write summation over D equals to 1 to C, probability of X belongs to T given the class information D, and then it is multiplied by prior probability Y equals to D. Okay. Now here node T classifies all the data which enter to this lymph node. Okay, which belongs to the class C, and this will minimize the estimated posterior risks. Okay, so here the node T will classify all the data that will enter to it, and it will minimize further the estimated posterior risks. So this is the posterior probability. This is the posterior probability of the posterior probability of the data that belongs to class C given the data that enters lymph node T. Okay. So now this is our classification decision. So here we estimate the posterior probability, and this posterior probability will give us the classification decision. Now what after this, what we do, we need to minimize this function. Okay, now this function is posed as the minimization function, so we need to minimize this function so that the risks will be further minimized and we can get the optimal value. Okay, so how it can be done? So for that we can write, so you are familiar with this minimization of functions when we are discussing base classifier, naive Bayes classifier, as well as the likelihood methods. Okay, so this is the familiar term for you. So we can write R of C given X belongs to T. This is given by summation over loss function L of D comma C, which is multiplied with this posterior probability that we have already estimated for a certain class in. Okay, so we can write this. So summation over, this is the L of DC is the loss function. Okay, and which is multiplied with the this posterior probability, and this will give us the risks of this classification decision. Okay, So here we try to minimize the function so that uh, we can get the minimum risks, and that will also determine the optimal value for this classification decision. Okay. Now, when we are talking about the classification trees, so one important term that we can use frequently when we talk about the classification problems which are to be implemented using decision tree or some other classification trees. Okay, so the we can use the term impurity. Okay, impurity of leaf node or impurity of any other node that we have to decide when we will design the classification tree. Now, what is impurity of leaf node? So when we see the data that enters through the root node and propagated through other non-leaf nodes, and at the end we get the leaf nodes, and leaf node assign assign a class label to the data. Okay, now suppose we are having an unknown example, capital X. So this is unknown example. Unknown means we do not know the class information. So what we need to determine the class information using decision tree. So this is posed as unknown to us. Okay. Now what we do, we will enter this data. We will enter this data through the root node. Okay. Since here the decision tree means we have already implemented the decision tree, and we have already made the trend model of the decision tree. Now we are using that trend model to classify this unknown sample X. Okay. Now what we see at the root of the decision tree, the impurity of the node will be found to be high, because we don't know about the class information of this unknown sample. That is why what we assume, or what we found, that the impurity of the root node is found to be very high. Okay, so when it is gradually propagated through the intermediate node or the non-leaf nodes, and when it goes to the leaf node, so at the leaf node you will see the impurity of the leaf node is found to be very high. Okay, so no, okay, sorry, so purity of the leaf node is found to be very high than the impurity of the root node. Okay, so if we consider this is our decision tree. Okay, so in this way we can get the decision tree. Now at the root node the impurity will be high, at the leaf node the impurity will be very low. Okay, that means whenever we enter the value of this unknown sample through this root node, then at the root node we do not have any information about the class or the level of these unknown examples. So when it is gradually moving or propagated through these non-leaf nodes or the internal nodes to the leaf node, so at the leaf node we will have the purity of this unknown example X. Okay, that means the purity level of these unknown examples will be found to be very high at the leaf node. Okay, because at the leaf node we get the class information, or we get the level of this unknown sample. That is why we get the purity of the leaf node for the unknown example. Okay, so now how to estimate the probability of this probability of a leaf node. for which the impurity of the lymph node for which the purity is found to be very high. Now let us consider so similar to the classification decision. So here we can estimate the posterior probability. Now posterior probability of what? So posterior probability of the data that has that might have a different class information. So we can represent this impurity of a lymph node by probability of y equals to 1 given capital X belongs to T. Okay, y equals to C given X belongs to T. So this is the impurity. So here we measure the impurity of lymph node. Okay, impurity of lymph node. So this posterior probability will give us the impurity of lymph node. So here we measure the impurity of the lymph node by estimated the posterior probability. Okay, so now there are few questions so that we need to answer or that we need to understand for implementing a decision tree. Now, the first question that we can ask, how to decide which feature should be located at the root node. Okay, so this is a very big crucial question. So if we are dealing with n number of attributes or n number of features, then for a particular feature so how we can decide the root node in the decision tree. That means we may have x1, x2, xn, so n number of these are the features or attributes. If you know the table in a database, then you can see that table may contain a number of attributes. Okay, and those attributes are having a set of values. Okay, set of values means those values are homogeneous for a particular feature or particular attribute. Okay, similarly here we can have a set of, let's say, p number of homogeneous feature. Okay, here we have p number of homogeneous feature. So this feature this set of values are found to be the same dimension for x1 to xn. Okay, now the first question that we try to understand, how to decide which feature should be located at the root node. Now since we are having n number of features, n number of attributes, now when we construct a decision tree, when we construct a classification tree, now from which point we should start. That means which feature or which attribute will be located at the root node. Okay, that means which feature will be the root node or which attribute will be the root node among n number of features. So that is a big issue. So using the splitting parameters or splitting constraint, we can get this answer. Okay, that means we can decide which feature or which attribute will be the root node of the classification tree. Okay, now if I look at the second question, so which would be the most accurate feature to serve as internal nodes or lymph node? Okay, so how we can decide this? As I said earlier, that we can have some splitting parameters. So using splitting parameters, we can decide so what will be the non-lymph node and what will be the lymph node. Okay, that means if the if the input data is propagated through a number of steps through across the non-leaf nodes, then obviously the non-leaf nodes will be responsible to decide through which along which branch the data will be propagated. Okay, and that can be done by using splitting parameters. Okay. And the similar questions we can have how to divide the tree. So as I said, the splitting parameters we can use to divide the tree into different branches. So now we will be talking about the splitting parameters or the splitting constant based on which we can split the decision tree into a number of branches, and these splitting parameters will help us to get the correct class level of some given example. Now, first such splitting parameter is entropy. Okay, entropy. Then we will talk about the information gain. The second one is information gain. Okay, and third one is Gini index. Gini index. Okay, now using these three splitting parameters, entropy, information gain, and Gini index, we can further split the decision tree into a number of branches. Okay. Now, for your information, this entropy and information gain, both these splitting parameters are used in a particular variant, which is called ID3. ID3 means the iterative dichotomizer 3. This is one variant of decision tree. Okay, so only these two splitting parameters are enough to split the decision tree, which is based on the idea of ID3. Okay, ID3 variant. And when we use the three splitting parameters, then we can use another variant, CART. CART. This is another variant of decision tree. Okay, so in this decision tree, we need to use these three splitting parameters, or we can skip this information gain and we get the Gini index in place of information gain. Okay, but in ID3 and C 4.5, both these variant use entropy and information gain, and another variant CART uses these three splitting parameters. Okay, now what is entropy? So when you talk about the entropy, so entropy, what entropy gives us? So entropy gives us the measure of the amount of randomness or uncertainty. Okay, so since there is a set S of data, then we can get the entropy of this dataset S, which is given by summation over probability of small x. Okay, log of 1 by probability of. So you can you are familiar with this equation. This is the equation of the Shannon entropy. Okay, Shannon entropy, and this entropy will give us the measure of the amount of randomness or uncertainty. Now about the feature for which we are interested to have the measurement of the randomness or uncertainty is the feature. Okay, since we are talking about n number of features, therefore we will get the probability of a probability on a particular feature xi. Okay, or we can say just x that belongs to capital X. Okay, so here capital X belongs to, we can write r to the power n dimensional. Okay, Here x is the n-dimensional feature vector. So for a particular feature x that belongs to capital X, we can get the entropy by taking the summation over probability of x multiplied by log of 1 by probability of x. Okay. So this equation of Shannon entropy will give us the measure of the amount of the randomness and uncertainty. Okay. Now let us take an example. When we toss a coin, the probability of head is found to be 0.5 and probability of tail is found to be 0.5. So can you tell me what will be the entropy of this distribution? The event is, what is the event? Event is when we flip a coin, okay, in the air, then either we will get the tail or we will get the head. Now the probability of getting head is 0.5, probability of getting tail is 0.5. Okay. Now at this stage, so we don't know. So what will be the predictability of this event? Okay. So here event is the coin toss, and we don't know about the predictability of this event. So that is why we are seeing the probability of getting tail is 0.5 and probability of getting head is 0.5. Okay. So here the entropy is found to be perfect one. Entropy H of S is found to be perfect one, because here we are having the uncertainty of the predictability of the getting head and getting tail. That is why the entropy is found to be perfect one. Okay. Here the uncertainty is or other way we can say the randomness is found to be high or uncertainty is found to be high. Okay. Now suppose when we flip a coin and we get both the sides are head or both the sides are tails, then the randomness is found to be 0. In that case, entropy is found to be 0. That means in other way we can say that the uncertainty or randomness is found to be very low. Okay. So before flipping the coin, so we can easily predict what is going to get. Okay, that means if both sides are found tail or both sides are found head, then before flipping the coin we can easily tell so what is going to we get. Okay, so this is the entropy which is considered as the spreading parameter. So using this parameter, we can get some information about the data that is entered through the root node and propagated through the internal nodes. Okay. Now another parameter that we can use, which is called information gain, or short we can write IG. What is information gain? So information gain denotes the relative change in entropy. Relative change in entropy with respect to some parameter or with respect to some attribute or with respect to some feature. Okay. So information gain is given by Ig. We can write Ig S comma A. Here capital S the data set. Okay. Capital S represent the data set and capital A represent the attribute. So therefore, in terms of dataset S and attribute A, we can write Ig of S comma A, which is given by Hs. Okay, H of S, entropy of dataset S, minus we can write H of S comma A. Okay, so here we subtract the entropy of the data set with respect to some attribute A, from this entropy of the entire data set. Okay, so we subtract the entropy of the data set with respect to some attribute from the entropy of the entire data set. Okay, and further this can be derived as h of s minus, we can write I equals to 0n probability of x. Here x represent a particular feature or attribute, and h of x represent the entropy of that feature. And what is n here? What is I here? Here I here we are taking the summation for I equals to 0 to n. What is I here? So I represent a particular value of that attribute. Okay, if we are having n number of okay, if we are having n number of class information, let's say this attribute will have, based on this attribute we can have n number of classes. Okay, so how many times this summation will be computed? So n number of times. If we have two different classes which can be determined based on for this particular attribute a, okay, or particular feature x, then we can have here I equals to 0 to 1, because there are two class informations. If we have n number of class information, then this summation will be computed for n times. Okay, or if we have four number of four different classes, so over these four different classes we will compute this summation four times. Okay, so therefore, in other way, we can say that the effective change in entropy after deciding on a particular attribute. Okay, or simply we can say that the relative changes which are measured in entropy with respect to some attribute or feature A. Okay, so today we will stop now, and we will be talking about Gini index and more on information gain in the next class. And in the next class we also take an example, and we will see how we can classify an unknown sample and put a class level using decision tree or classification tree. Okay, if you have any questions you can ask me, otherwise we will stop now. If you have any questions you can ask me. Okay, so that's all for today.